How to represent geometric objects is a fundamental part of computer graphics. Geometric objects. A point is a fundamental geometric object. It specifies a location in space. A mathematical point has neither a size nor a shape. Point alone is not sufficient to describe geometric objects. We need other values, such as scalars. Scalars can be real values or complex numbers. They are used to specify quantities. They obey a set of rules, such as addition and multiplication, commutativity and associativity, multiplicative and additive inverses, and so on. Another geometric object used in computer graphics is a vector. A vector allows us to work with directions. It is any quantity with a direction and magnitude, such as force or velocity. A vector does not have a fixed location in space. Instead, it is just a direction. Consider this vector which starts at point Q and finishes at point P. This magnitude refers to the magnitude of the vector, and the direction is the direction of the vector. All these vectors are the same vector. They do not have a specific location in space. Notice that all of them have the same magnitude and all of them are pointing towards the same direction. Hence, they are the same vectors. Vectors can also be altered mathematically, similar to how scalar quantities can be altered. For example, here we have a vector A which has been multiplied by 2, and we get a vector that points exactly in the same direction except that it has twice the magnitude. We can add two vectors. Here we are adding vector A and vector C to get another vector that is D. The addition of vectors you must have studied in your high school is that we put the head of one vector to the tail of the other, and then we join the starting tail to the finishing head of all the vectors that we want to add. Adding two vectors changes our direction or can change our direction, and it also changes the magnitude. We can have a negative of a vector, which is a vector of the same magnitude but pointing in the opposite direction. We can add a vector to a point. Here, adding the vector v to a point Q moves it to the location P. When we think of a geometry, we think of it free of any coordinate basis. We can specify a geometric shape without having to specify a coordinate frame, such as a square. This square still remains a square whether or not we have a coordinate frame, and we can still refer to its points in one way or the other. However, having a coordinate frame makes it easy to refer to the different points and locations on this square, such as this point is 1, 1 in this coordinate frame, and this is the 0, 0 location. Similarly, this point is 3, 3 in this coordinate frame. The basic message to understand here is that geometric shapes are independent of coordinate frames, but however, if we specify them in a certain coordinate frame, it makes it easy for us to refer to its different locations, to refer to certain magnitudes, and also to manipulate them, which we will see in the later slides. If we view scalars, points, and vectors as members of mathematical sets, we have a variety of abstract spaces for their representation and manipulation. We start with a set of scalars, any pair of which can be combined to form another scalar through two operations called addition and multiplication. The most important space is the linear vector space, which contains scalars as well as vectors. In this space, we can combine two scalars, scalars and vectors, and two vectors using addition and multiplication. In a linear vector space, we do not have any way of measuring a scalar quantity. A Euclidean space is an extension of a vector space that adds a measure of size or distance, allowing us to define such things as the length of a line segment. An affine space is an extension of the vector space that includes an additional type of object, the point. Although there is no operation between two points or between a point and a scalar that yields a point, there is an operation of vector point addition that produces a new point. Alternatively, we can say that there is an operation called point-point subtraction that also produces a vector. In these abstract spaces, objects can be defined independently of any particular representation. They are simply members of various sets. One of the major vector space concepts is that of representing a vector in terms of one or more sets of basis vectors. Many geometric concepts that relate the orientation of two vectors are defined in terms of their dot and cross products. Dot product is also known as the inner product. The dot product of two vectors is always a scalar. For example, the dot product of u with itself is the square of its magnitude, which is a scalar value. The dot product of two vectors which are orthogonal to each other is 0. The dot product of u and v, any two arbitrary vectors u and v, is given by this relationship. So it's basically cos of the angle between the two vectors and the magnitude of the two vectors multiplied together. The orthogonal projection of vector u on v is given by this relationship. Cross product of two vectors is defined with this equation. The cross product of two vectors will give a third vector that is defined by the right hand rule. For example, u, v, if you point your fingers of your right hand from u to v, then u cross v, the resultant vector of u cross v will point in this direction where your thumb points. This will always be normal to the uv plane. So if we want to find a vector that is orthogonal to u as well as v, all we need to do is to take the cross product of u and v. This will be orthogonal to the plane that contains the uv vectors, and recall that only a single plane can pass through two vectors that are non-parallel.